We have one section, not even a section, one topic left. Okay, I would like to do a binomial, a Maclaurin series for expanding a binomial. And so we've seen, usually we write it the other way around, like x plus 1. Certainly you can recall x plus 1 to the first power, right? A line. Played with that back in the very beginning of algebra, and then we squared it. And so squaring a binomial, and that took quite a long time. It was trying to remember the middle term. And then cubing a binomial and 4th degree and 5th degree and 6th degree. And you probably recall that there was a quick way of getting the coefficients, right? Do you remember this? Is this sounding familiar? If I need, I'm going to write it this way because it's more familiar. Like x plus 1 raised to the 4th power. Then I know that this is going to be a 4th degree polynomial because I'm going to have, well, because basically I'm going to have an x plus 1 times an x plus 1 times an x plus 1 times an x plus 1, right? So every one of those times every one of those, distributed property lots of times. So basically I'm going to end up with the x times the x times the x times the x, and I'm going to end up with an x to the 4th, right? And then at the end, I'm going to get a 1 times 1 times 1 times 1. So way down here, I'm going to get a 1. And then we just got to figure out what terms go in the middle. And so it turns out that they're all positive, right? So there's going to be some number, right, of x cubes, and then some number of x squareds, and then some number of x's, right, that kind of go in the middle here. So what we're trying to do is find the coefficients that we would need when we expand the binomial. And this works out pretty nice if you play with it a little bit, right? If you actually do the algebra and multiply it all together, okay, you end up with a kind of a pattern that develops, right? This pattern, right? 1, 4, 6, 4, 1. And so what you find out is that there are as 1 x to the 4th, right? There are 4 x cubes. There are 6 x squareds. There are 4 x's, and there's just 1 here at the end. Okay, and so this was called Pascal's triangle, and it's kind of cool. It produces the coefficients of this expansion of the binomial. And you can kind of play with this table. In fact, you can spend the better part of a semester just playing with this table. So there's all kinds of cool properties and relationships here. And then somewhere, I don't know if we did for you guys, we said there's a notation for this coefficient, right? And we said it was n choose k, right? In fact, for this particular one, it was, for this particular one, we're on a 4th degree, choose 2. 0, 1. 4th degree, choose 1. Because I'm pointing to that first one. So what's this one? This one's the 4, choose 2. Have you guys seen this choose notation before?
Maybe in a different notation, but no, I have not seen this specifically.
Okay. All right. Well, then that's going to be something that you're going to see in some other class somewhere down the road. And that's okay. I would say maybe a statistics class is the next time it's going to come up. So like a beginning statistics class or something in probability, okay, is where you're going to see it next.
I've seen the notation NCR where you say, hey, 4, choose 1.
Same. These are the same.
Yeah.
Okay, so that's the same notation. Well, this is all very lovely, but check this out. If I put an integer power on my binomial, then I'm not going to get an infinite polynomial, right? I'm going to get a finite polynomial because it's a finite number. So even though it's really big, we don't have an infinite series going on. We just have a finite one, which is fine. our little formula should work for ones that stop, and our little formula is actually better than that because it's going to work for ones that go on and on and on. But the cool part would be what happens now when I raise a polynomial to some other power, right? What about something like this, right? And so now you have something that looks like the square root of x plus 1, okay? Or even crazier, what if I raise a polynomial to the pi power? What does that even mean? How do I deal with that? Where does this show up? I mean, there's going to be some more cool places, right? You're going to see this again in a lot of cool places. But we want to just see, what if I just try to make a Maclaurin series for this thing? What if I try to turn this into a series, right? And so we should be able to, when k is a positive integer, right, the terms ought to go for a while, and then the rest of the coefficients should be 0 and they should stop. But what if k were, say, something like 1/2? Then we would get the square root function, and then we would basically be building a polynomial model or a series model for the square root function. All right, well, let's just do it and see how far we get. So f of x is equal to, and I'm going to write it sort of this turned around way, because we've been putting the larger and larger powers of x in our power series, on the right-hand side. So this is to the k power. K is any real number now. Okay, but it's a constant, right? You pick it, it's a constant. All right, so what do we need? We need the derivative, right? So we've got k, 1 plus x to the k minus 1. So it begs the question, how do I know that derivatives work, right? How do I know that derivatives work for all real numbers? In other words, if you're trying to prove something, you can't really prove something based on something you haven't really proved. So if we're trying to find the Maclaurin series, then how do I know this is the correct derivative? In other words, what if I have this, x to the pi, and I ask you this, right? Then you go, oh, I think that power rule still works. Power rule still works. Pi x to the pi minus 1. Power rule works. Yes, it does. How do I know the power rule works for real numbers? Anybody remember?
Didn't we prove that, like Calc 1?
We proved it somewhere back in the day.
I was trying to remember.
Y equals, I'm going to write x to the k, yeah? Where k is a real number. How do I get the derivative? There was a trick. It might come up on the final. It would certainly come up on a comprehensive, like year-long final. What's causing you the most grief? I'm thinking the exponent, yeah? If there's no exponent, we'd be done, wouldn't we? Maybe we could get rid of the exponent. How can I get the exponent off of an exponential?
Oh, natural log.
Okay, why don't I take the natural log on both sides? So then what do I get? I get something like k times the natural log of x, because power to a power, I multiply. Remember that rule? Now, if you don't remember that rule, then you got to go back and prove that rule. And that rule we proved way back in maybe Algebra 150 or maybe 187 or somewhere back there in the past. But I think that that one's true. Okay. Anybody kind of remember how to prove that rule? Power to a power? It turns out that the logarithm rules were hard to prove. So what we do is we turn the logarithm rules into exponential rules, and then we prove the exponent rules. Okay, we prove those. And then we just turn the exponent rules inside out, right? Since they're inverse functions. I'm not getting too many like, oh yeah, I remember that. That's okay. That's how you do it. So we know the rules, so we're just going to use it. All right, now what?
For
Now,
f of x, don't we just keep taking the derivative?
now we want to take the derivative, right, on both sides, don't we?
Yeah.
Because we were trying to find the derivative. Okay. All right, well, this is a chain rule on this side. So the log of something is 1 over the something times what? The derivative of the something, yes?
Mm-hmm.
Oh, you're going to see that a lot in differential equations, like every day. And now this side, what do we got? This is a constant times something, so the constant comes to the front. In fact, the derivative of a constant times something works for all real constants. It doesn't matter what the number k is, still comes to the front. So here comes the k. And the derivative of log of something, 1 over the something. But the something is just x, so the derivative of something is 1. So I think we're done over there. Now what? Well, now you get y prime on one side all by itself. Looks like y over x, k times y over x. But what was y?
X to the k.
It was x to the k divided by x. Okay, well, what do you do with power, with the powers when you divide?
Subtract.
Subtract kx to the k minus 1. Oh, that's kind of beautiful, isn't it? What does it depend on? Well, it depends on the fact that we can take the log on both sides of the equation. That's got to be legal. We never really proved that, but it seemed to work okay, so we've been doing it. You might want to prove it somewhere down the road. It depends on this exponential rule, right? The log of something to a power is the power times the log of the something. And that's got to work. That's got to work for all real numbers k. So you'd have to prove that this logarithm property is still a real property. We actually really did prove that back in the day. So that's not something hanging over your head. But if you forgot it, you might want to go back and look at it. Then what? Well, we got to be able to take the derivative on both sides of the equation. And that's got to be legal. So there's probably some prerequisites, like the functions have to be continuous, they have to be differentiable. So there could be some problems with the domain. Like we don't want to plug in, say, negative numbers for y here. But if you're going to prove that it's okay to take the log on both sides, I'm guessing at the same time or very in the same time frame, you're going to prove that it's okay to take the derivative on both sides. And the rest of this is just algebra. There's nothing else going on here. So those are just the rules and the properties of algebra. Some of which we proved, maybe some of which we just talked about. I mean, why can I multiply by the same thing on both sides of an equation, right? Why do I subtract the exponents? Okay, but these are things that we've been doing for quite a long time. And so I'm feeling like we pretty much got it. All right, so okay, I'm feeling like that's how you do that. That's called logarithmic differentiation, and that's a nice trick for you to kind of remember as you're heading down the road. Okay, there's the derivative. So what's the second derivative? Well, it's a constant times a function. So here's the constant. I pull that out to the front, and then you just use the power rule again. K minus 1, 1 plus x to the k minus 2. And then the third derivative, right? The third derivative is just a constant, right? Here's the constant times the derivative of the function. So use the power rule again, k minus 2 times 1 plus x to the k minus 3. And at this point, I think that we can see the pattern. Okay, so why did I take all this time to find these derivatives? Because our Maclaurin series, right? Our Maclaurin series is the sum, n equals 0 to infinity, of the constants, right, times x to the power. So this is the power rule. But for a Taylor polynomial, we know how to find the constants. So how do I get the constants? You take the nth derivative at a, right, and divide by n factorial. Okay, and if we're doing it in the general case, I can write the general case up here too. And of course, a in this problem is 0 because we're doing the Maclaurin series. It's centered at 0. So this is probably a really good thing to remember. The general power series and the general Taylor series. Okay, so here we go. I need these coefficients. So in they go. I'm sticking a, I'm sticking 0 into the function. So when I stick 0 in here, I get 1 plus 0 to the kth power. 1 to anything is 1. So I'm thinking the first term is 1. So P of x starts at 1. Then I stick in 0 into this function. So I get 1 plus 0 is 1. 1 to the anything is 1 times k is k. So I get k x's. Then I'm finding the next coefficient. So I stick 0 into the second derivative. And I get k times k minus 1 times 1 to any power is 1, x squared. Plus, I'll write it down here, I'm running out of room. I'll just wiggle down. K times k minus 1 times k minus 2, right? X to the third power. Plus, dot, 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 keep going. If you wanted to write that in summation notation, that'd be okay too. So how do we get it in summation notation? N equals 0 to infinity. Okay, so we're going to have x to the nth power. I'm going to put that at the end. I don't know how much room I need to save. And then what do we have here? We've got k times k minus 1 times k minus 2. So how do I produce this thing, right, in a formula? Right, that's a pretty good question. I guess you just have to write it all out, something like this. K times k minus 1 times dot, dot, dot times k minus n plus 1. In other words, stop, right? You don't go all the way down. You stop at 1 short of the 3. You go down to k minus 2, right? Stopping 1 short of the 3. And what's in the denominator? Oops, what is in the denominator? You guys said you went too fast. Here they are right here. They belong underneath here, don't they? So I forgot to write them. So I suppose we better get back in there and write them. What's underneath this one? 0 factorial, 1 factorial, 2 factorial, 3 factorial. There's my factorials. Forgot to put them under there. So then we've got n factorial, x to the nth power. Okay, there it is in summation notation. I kind of like it in the series notation in the expanded form because I can kind of see how it's developing as I go along. But again, we've talked about the fact that you might like it in one notation or another, or switch back and forth. Katie, did I make a mistake?
No, I'm just confused.
Okay, where?
So in summation form, you can put like dot, dot, dot in it?
That's a weird thing, yeah. There's a weird thing that there's a dot, 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 right? Because there's a dot, dot, dot inside of a sum. But look at this dot, dot, dot. This is a product. I'm multiplying k times k minus 1 all the way down to k minus n plus 1. So I'm stopping, right? 1 before the n. So yeah, that's a weird notation. It's like I put the whole point of the sum was to kind of get rid of the dot, dot, dot. And now I still need a dot, dot, dot inside of my sum. But there's a little bit of a difference, because here, this dot, dot, dot says, continue the pattern, but don't continue it forever. This is still a finite product. Okay, there's only a finite number of terms here. So it's a big difference between this dot, 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 meaning go on forever, and this dot, 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 meaning follow the pattern. Okay, so those are...
If you wanted to get rid of the dot, 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 like if they didn't want that, would you do a sum of a sum?
No, because look at what are you doing with these? You're doing what with them? You're
Multiplying.
multiplying them together. So instead of doing a sum, you'd do a product. So you'd write the product, and we use a big pi for product. Just like we used a big sigma for sum, you use a big pi for product. And let me see if I get this right, because I don't want to write it down wrong the first time. Okay, so maybe we say the product, and I'm going to use I, because I used to use I all the time, and then we switched to N. So I might mix it up. All right, I equals 0. And how far is it supposed to go? It's supposed to go all the way out to N, I think. Nope, it's supposed to go out to N minus 1. Because I want to stop 1 before the 3. I don't want to stop at 2. And then I would write K minus I. So this is the shorthand notation for a product, which is kind of cool. It means stick in I equals 0 and start with K. And then stick in I equals 1 and multiply your K, right? Because it's a product now. Multiply your K times K minus 1. Then stick in I equals 2 and multiply times K minus 2. Then stick in I equals 3 and multiply it times K minus 3. And keep going until we get to N minus 1, one smaller than the exponent. And then stop.
So that only expresses the numerator?
That, yes, that's just this product right here, right? This, I don't know, this thing, right? That thing up there in the numerator, right, is our product. So that's kind of shorthand notation for our product. So how could we write this? We could, since we could write this as the sum n equals 0 to infinity, 1 over n factorial, right, times the product now, holy moly, times the product, I equals 0 to n minus 1 of k minus I, and then you've got, that's the top, right, there's the bottom, and then we've got x to the n, so you might want some, maybe you need some parentheses around this, I don't know, to make it clear. Cool, huh? I didn't think anybody had seen an infinite product before, or even a finite product in product notation. And I thought that'd be kind of a fun thing to throw out there. So you can write sums and you can write products that go, this one, of course, stops at n minus 1, but it certainly does beg the question, can you have an infinite product? Can you keep going on forever and ever and ever? And if you did go on forever and ever, would it converge or not? I mean, I didn't want you to get the idea that because we're at the end of Calc 2 that there's no more math for you to study, right? These are pretty good questions that you could ask about as we go on down the road.
Well, yes, there could be one that converges. You just have to have a fraction of some sort in there.
Right on, that would do it. So a product, n equals 0 to infinity, right, of 1/2, right, to the nth power, one of just 1/2. Let's leave a 1/2. What is that saying? That's saying take 1/2 and multiply times 1/2 and multiply times 1/2 and multiply times 1/2, right? forever. What do you get? Half of a half of a half of a half of a half. Sounds like it's going to 0 to me. This would be a little bit more interesting, but if we did, we better not start at 0. Maybe we would go like this, maybe. And then we would say that's 1 times a half times a third times a fourth times a fifth times a sixth. That also sounds like it's going to 0, but even faster. Okay, so I'm just going to leave that as this is just a notation I thought I'd show you because I thought it was cool. Now, this whole thing inside here, this is getting a little messy. This whole k times k minus 1 times k minus 2 dot, 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 down to k minus n plus 1, right? All over n factorial. This has a special name. Okay, and so we call that the binomial coefficient. Okay, which is cool because of course these are the coefficients to our binomial series. And it's called a binomial because we have 2 terms and we're raising them to a power. So it's a regular old binomial. And what we're trying to do is find the coefficients, and this tells you the coefficients. And guess what? There's some really cool shorthand notation for that as well. Let me make sure I'm not lying to you. I don't think I'm lying to you. Okay, so everything is looking pretty good so far. So then there's some shorthand notation, and this is it. And it sounded like maybe Shane had seen that used in one particular way before. Okay, that's our notation that says do the binomial coefficient. When k and n are integer values, okay, and k is bigger than n, then sometimes we remember this as the choose function. Okay, so if I write something like this, if I write 5 over 3, then what I'm meaning is 5 things taken 3 at a time, okay, or 5 choose 3. So if that sounds familiar to you, awesome. In fact, we even have a way to compute that. Does anybody remember how to find 5 choose 3?
Yeah, use a calculator.
Yeah, exactly. You push it on a calculator, but there's a way to do it by hand. I think it's 5 times 4 times 3 divided by 3 times 2 times 1. Why? I don't know. Some other class, it's going to take at least an hour to explain this, or a week. Is that looking familiar to anybody?
Half of a factorial times the other half of the factorial.
That's correct. In fact, the denominator is the 3 factorial. The numerator is the
5.
first 3 terms of as you are going down. Like as a factorial, you're going down, but you stop. Just like this goes down, but it doesn't go all the way down to 3, 2, 1, right? It doesn't go all the way down, it stops. Okay, and that's the same thing that's going on here. So what would you get? I don't know, you get 20 in this case, I think. No, you get 10 in this case, right? And I'm kind of hoping that if we pushed it on a calculator and did 5 choose 3, we would get 10. So maybe it's time we do a little confirming now. So let's go somewhere to confirm some stuff. Here's some stuff I already built a little bit ahead of time so that you wouldn't have to watch me type it. But if I go over here, let's go to, I don't know, it doesn't matter really. I'm kind of thinking that Symbolab or Wolfram or Desmos or lots of things ought to have the choose function. But where is it, right? It's not, doesn't seem to be up here in my list. Or is it? Did you find it? This is a regular fraction, not a choose function. And so, right, I don't see it in here either. This seems to be the problem for me and Symbolab, is that I don't use it enough to know what the functions are, and I have trouble finding them. So I clicked over here on stats, and I'm looking over the side here, and then I'm clicking on probability, and then I'm thinking that if I pick probability, hey, look, it gives me some examples, NCR. I could have just guessed that it was NCR, okay, but I didn't know how to type it. And I find that Symbolab sometimes isn't real clear with how to type it. 5 NCR 3, 5 choose 3. What do we get? We get 10. And check it out, it gives you the formula for it right here. Is that big enough? Can you guys see it? Here, does that make it bigger? There, it's a little bigger. Okay, so n factorial over r factorial, n minus r factorial. And so I wrote what? I used K and N, and they used N and R. So the letters are a little bit different, but here's the calculation, right? And it comes out to be 10. And boy, I think you're going to see that again somewhere coming down the road. Okay, but here's the big deal. This all should make sense in terms of counting a whole number of things. In other words, integers. It should make sense for integers. But what on earth would, if K, right, we were said K could be any real number. So what do I do if I do a half choose 2? How do I say 1/2 choose 2? You can't choose 2 from a half, right? There aren't 2 to be chosen. You've only got a half in the first place. And so what does this mean? And the answer to what that means is what we have just been talking about, okay? It does work, and how, right? Kind of the way we've been looking at it. We're gonna have to convert it into a series and see what's going down. Okay, so that's a little introduction to that stuff. Let's look at Desmos and see what this thing all pans out to be. So here is our binomial. So this, let's turn that off. So here's how we start. F of x is 1 plus x to the k power. Here's this black function. Can you guys see it? Yeah, okay. And I want to just explore k as 1/2. Because if we can do it for k equals 1/2, then I'm kind of thinking we could do it for k equals 1/3 or 2/3. And then maybe it wouldn't be a big stretch for pi and e. So when I stick in 1, I get 1 plus 1 to the ½ power, √2. Everybody okay so far? Okay, so what do? We build our Maclaurin series. That's going to be centered right here at 0. And we try to model this function using a series instead. So this should look familiar. There's the derivative with 0 stuck in. No, there's the function with 0 stuck in. There's the derivative with 0 stuck in. There's the second derivative, right, with 0 stuck in. There's the third derivative. So I'm hoping that this polynomial looks pretty familiar. We just built it. And as you can see, it's fitting pretty closely to our square root function that we were trying to model. So right in this range, it looks really good. Now over here by 1, when we wanted to estimate √2, it's still not looking so good over here. But right close to 1, or right close to 0, x equals 0, it looks really good. So what should we do? We should make some more terms. And so I want to make a lot more terms, but I want to write this in summation notation. And so check out what I did. I need the coefficients. So here are the coefficients. And it's 1 over, I needed some new letters. I can't use K and N because I already used them. So I just called them K1 and N1. So some dummy variables to hold a spot. And so then I wrote 1 over N1 factorial. There's the denominators. And check out the top. The top is a product. I goes from 1 to N minus 1 of K minus I. Right? Just like we just wrote. So this little formula will produce the binomial coefficients. In other words, the numbers before the x to a power. And so if I want to write the whole thing, then I can just say my polynomial is my sum, n goes from 0 to m, of the binomial coefficient, right, times x to that power. I can turn it on, And then you can see here's the third degree, there's the fourth, fifth, sixth, seventh, eighth, right? And so out here somewhere around the 10th one, notice that it's fitting better and better and better. We're getting a better and better estimate. But I'm still having a little trouble right here near 1 because I suspect that the interval of convergence, right, for this function is from where to where?
Half to a half.
Now I'm thinking a little further.
-1 to 1.
-1 to 1. So I'm kind of thinking that if I want root 2, that this isn't going to work so well because it doesn't converge when x equals 1, right? It's just like right on the end where it's starting to bend away. Sure, if I wanted the square root of, you know, a quarter or an eighth or something, it would be great. But out here at 1, it's not looking so good. Okay, but you can see that as I add more terms, I get a better and better model, right? And it fits really, really well through this range. Okay, so what should I do? Well, if I really need root 2, then what I really want to do is not model my function around 0, but I want to model, say, my function around x equals 1. Because if this was fitting good right around x equals 1, then I would be able to know what root 2 is, right? Because it would fit really well. So what do? All right, and you guys should know that. Now I need one centered at x equal, or a equals 1. So what's my, so here's my function. F of x equals 1 plus x to the k power. But instead of plugging in zeros now, you know, then find the derivative, then find the second derivative. But instead of plugging in 0, what are we going to plug in? A, right on. In our case, if we want it to be centered at x equals 1, we're going to put in 1 now. Is that making sense?
Mm-hmm.
So now you got to find f of 1, f prime of 1, right? F prime prime of 1. Well, what do those look like? When I stick in 1, I get 2 to the k. When I stick in 1 into the derivative, I get k times 2 to the k minus 1. Right? Because I'm sticking in a 1, right? And then what about this one? I get k times k minus 1 times 2 to the k minus 2. So this is way more complicated because remember it was just 1 to the k and 1 to the anything is just 1. So these all kind of went away. But now that it's not 1, I've got these powers of 2 that are hanging around. Notice that I still get the same, you know, k times k minus 1 times k minus 2 in the front. Okay, so without going through every single detail, I know that was teeny tiny off to the side, sorry about that, but Desmos is still up in front of you. So without going through every teeny tiny detail, I want to model over here at x equals 1. So check out what I got. This is going to be my, my new model. So here's my new model. This is the function at 1, what I get when I plug in a 1, right? It's right there, we just did it. And then this is what I get when I plug in 1 into my derivative. But now I don't just have an x to the first, I have an x minus 1 to the first because I've shifted my polynomial over. Okay, here's what I get when I stick in 1 into the second derivative, right? I get k times k minus 1. And then I get this factor of 2 times k to the, or 2 to the k minus 2 power. And so check it out. This is fitting really well over here at 1. Doesn't fit so well over here at 0. In fact, what do you think that the interval of convergence is for our new function?
0 to 2.
0 to 2. It's still going to have an interval of 1, or a radius of 1. It's only going to be 1 in radius, but it's going to go from 0 to 2 now. So it's not going to fit so well over here, but boy, it fits good right around here, which is great because when I stick in a 1, I want to get 1 plus 1 to the power. I want root 2, right? Okay, so if this is our second degree one, then what would you do? Third derivative, fourth derivative, fifth derivative, sixth derivative. I went ahead and just wrote that in summation notation. It looks exactly the same as our p polynomial. It's got the binomial coefficient. It's got the powers. It's got the function raised to the nth power, but it's got these extra factors of k to 2 to the k minus n powers. And here they are. Let's see, as I change m, okay, as I change m, you can see that it's fitting, maybe I'll zoom out a little bit. You can see that it's fitting better and better and better and better between 0 and 3. It's between 1 and 3, yeah? Does that make sense? Okay, so what's this? This is a Taylor series. Taylor is more flexible than Maclaurin, right? Because we can say x minus a to the power. So we can shift it left and right. How are we doing so far? Everybody still pretty happy? Okay. I was thinking, though, that there might be an easier way to get root 2. And instead of expanding 1 plus x to the k power, what if I expanded 2 plus x to the k power and then just did a Maclaurin series? Because then I could plug in x equals 0 and I get 2 to the k, I get 2 to the 1/2, I get root 2. So instead of looking at f, maybe what I could look at is a new function g. Okay, so what's so special about g? It's 2 plus x to the k. So right here, when I plug in 0, guess what I get? Root 2. Yeah, that value right there should be root 2. Is this making sense? Okay, so I wanted to show you that even though we modeled 1 plus x to the k power, there really wasn't anything special about the 1. We could have put a 2 in there, or 5, or any other constant. And so how do you do it? You take the derivative. You first plug in 0 and get 2 to the k. Then you take the derivative, plug in 0, right, and start building your polynomial. Here's the linear polynomial, right? So what would the next term be if we added a term? It would be k times k minus 1, 2 to the k minus 2. How do I do that? I have to do 2. I have to back up. Yeah, k minus 2, right? And then it's x to the second power. And there's my quadratic that fits pretty well. Okay, and so if you did lots of terms, you would get something like this. And then as m goes up, what's that? That's about 18 of them. Look at how well it's fitting. Then if I do r of 0, woo, that's pretty close to root 2, yeah? Okay, so what's the point? The point is that if you've got a function and you're having trouble working with it, then you can replace it with a series, at least where the series converges, right? It's going to have to be differentiable. It's got to have to exist and all that kind of good stuff. But from time to time, it's going to be easier to work, this seems weird, but easier to work with an infinite series than it is to work with a messy function that you can't get your head wrapped around. Okay, so this comes back to our age-old trick, which is if you got something that's causing you grief, write it in a different form, right? Replace it. Okay, and sometimes what we do is replace it with a series instead. I really like the, I would have been remiss to not get to the very last day and not scramble through a bunch of stuff that you didn't have time to all, internalize. Because every class always ends that way, right? We always end with a bunch of stuff that's right on the edge and we don't have time to really look at it really closely. So I think today there was a whole bunch of stuff that's pretty interesting because this particular function, expanding a binomial, has a lot of implications and shows up in a lot of classes as you come down the road. In particular, I think you'll see it in probability and statistics will be probably your next two places that you see it. But it certainly is going to show up quite often. And so I thought that it might be nice for you to just get a peek at it so that it's not brand new if it shows up again. But no, you don't really need to know, too much about it. I just wanted you to see it before you were done. Okay, so that's it. You've got a little quiz to take. It's going to ask you to write out some Maclaurin series representations of some functions, basically the ones that we did on our little activity together. And then it's going to ask you to say, take the derivative of some series term by term, take the integral of some series term, term by term. And then if I give you a function, I'm going to ask you to find the Taylor polynomial representation of that function. Okay, so doing exactly what we did the last couple of days. And then that is all for chapter 11. And so the chapter 11 will make up just one very small part of the exam. Right? The exam's going to go all the way back to derivatives that you should know. Okay, because that's where we started with 30 derivatives or so that you should know, have memorized. And then we said, okay, now let's talk about antiderivatives. And we found antiderivatives for a while. In fact, we found a bunch of them in chapter 5, and then we learned more techniques for antidifferentiation in chapter 7. And then most recently, we learned some techniques for antidifferentiating by first writing it as a series and then antidifferentiating. So a big part, like half or more of the test, is just finding integrals. A little bit of the test then are just odds and ends. And unfortunately, we had to put applications of integrals in our odds and ends category. I would have liked applications of integration to have made up a bigger part of this class. So we saw some in chapter 5, where we were finding the area under a curve. We saw some more in chapter 6, where we did area between curves, and then we did all those volumes. So volumes of solids of revolution. And I would say that was those were our two biggest applications of integration that we had seen. Area under a curve and volume of a solid of revolution. So my guess is that you'll get a few of those. There were a whole lot more applications in chapter 6. In fact, we could have talked about work and partial pressure and center of mass, and then even more in chapter 8, where we could have talked about arc length and surface area and lots of ones from business and other disciplines. Okay, so we didn't get a chance to explore the applications quite as much as I had hoped, but I think that you're so well grounded now in the mathematics that as you see those applications in your other classes, you'll be able to pick up on them pretty quickly. So if you're taking a physics class and you're talking about how much water pressure increases with depth, I think you'll be able to see where the integral comes from. And that should be pretty easy for you to pick up. Then after all of that anti-differentiation, all that integration, which was 3/4 of the class, we finally gave over to looking at series, sequences in series. And that's been so recent that I wouldn't worry too much about studying that. That's just been in the last few weeks. So that will make up, a small part of the exam as well. I'd say maybe 1/4 of the exam will be on sequences and series, the things we've been doing recently. And it's not like those were brand new, because of course a Riemann sum was an infinite series right from almost day 1 of this class, way back from the very beginning. So I think that if you've been playing along, and you guys really have, you guys have been outstanding, that I think that by its very nature, it's been so cumulative as we've gone along, other than just going back and brushing up on a few things that maybe you want to have memorized. I think that you guys should be ready to take the test. Okay, any questions about it? Yes, Katie.
It's not really about the test, but I know the end of the semester is coming up, and some of my other classes have like physical books that I
Okay.
rented. What do I do about that if I rented a book?
Check on the school website. I just saw something about like returning technology, like, you know, if you'd borrowed a calculator or something, or a computer. And so they had some directions about a day they're going to have pickup and that kind of thing. I would think that there's probably the same for the book. Did you get it through the bookstore?
Yeah,
Or
I did.
through the bookstore? I would probably look on the school website, and if you can't find anything for the book specifically, I know you'll find some information about how to return technology. And then call those folks and ask them, and then they'll tell you what the best thing to do would be.
Okay.
Okay. Other questions?
I was actually wondering if we could go over a problem from section 11.
Okay.
It's problem number 4.
All right. Problem number 4. What's it say?
I don't have it pulled up right in front of me. Just give me 1 second. And
Okay.
I
So
can.
you can pull that up, and then I'm going to take any other questions about, no, administrative stuff, test stuff, right? It's going to be on Wednesday. It's going to be, I want you to come sign in on Zoom, say good morning, and then you guys can get started, right? So that way I can kind of be available if you have any questions, and I can kind of proctor along as you go. But it's going to be open from 8 until noon. So you got 4 hours. And I think it should take you 2 hours, right? So you should plan on it taking about 2 hours. But if you want to go really slowly or take a bunch of breaks and get a sandwich or something in the middle, then you can take up to 4 if you like. Okay, but I do need you to get it done on Wednesday, unless there's like some kind of crazy emergency or something, in which case you better let me know right away. Okay, and then all of the homework is due, what did I say? Tuesday night at midnight, right? The night before the test, because I had to cut it off somewhere. So you can keep working on it, adjusting, getting a few more points as you're studying up through the night before the test. Okay, anything else administrative? Not seeing any. How about this question? What do you got, Curtis?
All right, so kind of 2 parts. First part, f of x equals sine x.
F of x equals sine x, okay.
A equals pi over 6.
Okay,
N equals 4. And x is between 0 and pi over 3.
x is between 0 and pi over 3. Okay, maybe including the endpoints or not, I don't know.
It is including the endpoints, yeah.
Okay, with the endpoints, okay.
So the first part, it wants to approximate f by a Taylor polynomial with degree n at the number a.
Okay, so we need sine x at pi over 6.
Mhm.
Okay, so how do we do that? We got to use this formula, right? So here's our polynomial. So you should write this down a few times until you've got it kind of memorized, right? The nth derivative at a over n factorial times x minus a to the nth power, right? That's what we're trying to do. So we know a is pi over 6, so you can plug that in. And so we can write out all these terms if we can find the derivative and plug in pi over 6. So let's do a few terms. Here's the first derivative, right? Derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine. The derivative of fourth, right, of minus cosine is back to sine again. And then it goes around and around. So what do we need? We need our function at pi over 6. So what is f of pi over 6? Sine of pi over 6. Is that a half? And then we need our derivative at pi over 6. So that's cosine of pi over 6. That's root 3 over 2. And then we've got our derivative, our second derivative, oops, at pi over 6. Second derivative, that's minus sine, so that's minus a half. And then we've got minus root 3 over 2. And then we're back around to a half again. We doing okay? Okay, then let's write it out. So what does our Taylor polynomial look like? I'm going to write it in expanded form, and then you can write it in summation notation too if you like. It's 1/2, right? 1/2 over 0 factorial, this stuff to the 0. And then you've got plus root 3 over 2, right? That's the numerator. 1 over 2 factorial. Nope, this is only the first term. 1 over 1 factorial, right? X minus pi over 6 to the first power. And then we got the next one, minus 1/2. And then we've got 1 over 2 factorial. And then we've got x minus pi over 6, right, to the second power. I'm going to write one more. Minus root 3 over 2 times 1 over 3 factorial times x minus pi over 6 to the third, to the third power. Plus dot, dot, dot. So what does that look like? Well, in summation notation, it's hard to write it because these coefficients are going around in a circle, and I don't know how to write a formula for them. So I would just leave it like this. All right, that's the first part. What's the next part?
Well, the answer is wanting it's t sub 4 of x. So it's wanting like a
you want
an actual
I'm sorry,
expression.
not t, right? You wanted a Taylor polynomial, and you
Yeah.
wanted the one that goes with 4. I don't know if this is, you have to go look this up. I don't know if this means the 4th power or if this means with 4 terms. Because if this means with 4 terms, there's 1, 2, 3, 4, you'd stop right here, you'd be done. If this means the 4th power, then we need one more term, right, for the 4th power. So it depends on if this means the 4th degree polynomial or the polynomial with 4 terms in it, right? And so that's just a matter of understanding what the question is asking. So I think we're both basically done. That's it.
Okay. So then the second part, it's wanting to use Taylor's inequality to estimate the accuracy of the approximation.
Oh, yeah, skip that.
Skip that?
Yeah, because that's basically saying, what we're saying is, how big, right, is this dot, dot, dot? Right? We're saying, what's going on here? This, if I stop at 3, then I don't get the exact answer, right? Because I need the dot, dot, dot. The dot, dot, dot is the rest of the polynomial. And that error that we have should be getting closer and closer and closer to 0 as I have more terms. So the question here is, well, what if I try to approximate sine x using this, right, with only 3 terms? How accurate is it? And Taylor came up with an estimate, a formula for describing the error. Okay, it's called the remainder, maybe the Taylor remainder theorem or something like that. And we didn't do that part. So if, you know, for our purposes, probably the best thing that we could do is put your 3rd degree polynomial in, put sine in, and look on Desmos to see how close they are. Okay, but if you want to dig a little deeper, then Taylor described how big is the error. Okay, and that's called the remainder theorem. And you can look at that, but we never did it. So, so you could skip that part.
Okay. As far as finishing the homework, what should we do for those parts? Because there's like 2 more questions on the, there's like 2, I think 3 of the 6 that were on the 11 homework were like
Have
that.
to do with remainder?
Yeah.
Interesting. Yeah, I don't know what to do about that. That's a good question. I don't think it's going to matter. Is what I would say. So if you're interested, dig around there and fuss with it a little bit, but beyond us, right? Beyond the class, so not on the test. So only do it if you're ready, feeling ready for your test and you're still curious. Otherwise, just don't do it. It won't make a difference in the end. Okay, what else? Is this the one you were asking me about, or is there still one more problem hanging out there?
There was that one more. That was from section 10, and that wasn't really, I guess, it wasn't really a conceptual question. It was more just a technical question.
Okay, so why don't you send me the number, that one's number, and why don't you send me the number of these three that I never talked about?
Okay.
For those of you that want 100% exactly on the homework, I will go figure out how to give you credit for these. Right? I don't know how to do it. I don't know if it will let me delete them from the homework assignment now that you guys have started or not. It might. And if it does, I will. And if not, then I don't know. I'll try to figure out. But in the end, it doesn't matter if you miss a couple of homework questions at the end. It's not going to affect your grade at all. So, but I know that some of you wanted 100 right on the nose. So send me, send me the numbers of these problems from this section, and then send me the one from 10, and I'll go try to figure out what they were asking.
Okay, thanks.
Okay. All right, anything else that I can tell you today before you head off to study? All right, I'm gonna let you go. You guys have, good luck studying. If you do get stuck or frustrated, make sure you give me an email or something, and I will try to help, okay? And otherwise, we will see you on Wednesday.
Sure.
All right. Oh, are we still having a meeting on Monday just for any last minute questions or no?
I can be available during office hours. How's that?
Okay.
Or at any other or most other times via email, but no more class meetings. That's it. So we're not coming back together again as a whole group until Wednesday. Katie.
If I happen to have like a last minute question on Tuesday, what are your office hours on those days?
Good question. Send me an email and I'll just answer you. Or I could just open the Zoom up and we can talk. I will be grading and I got to write another final for statistics. And so I'll be in and out around the computer. So what I'll do is I'll probably leave. Normally my office hours are 11:30 on Tuesday and Thursday.
Okay.
But I'll be here most of the morning, like every day. So, if you send me an email, we can just find a time, or I can just write you back, or we can just open up a Zoom meeting and talk.
Okay.
Yeah, and that's true for all of you guys. You're always all welcome at any time. Okay, is that it? Kevin's been quiet. Any questions, Kevin? Nope, shaking his head. All right, well, if something comes up, please let me know. Kevin, do you ever see Leo?
No.
Okay, I know you guys are back there sitting together, but I haven't heard from him for a while, and I was worried he might have disappeared. So if you guys hear from any classmates that haven't sort of got the word, and they're like, hey, when's our test, that kind of thing, make sure you let them know, okay? Because I want to try to get as many people, on the right track as we can. All right, other than that, that's it. You guys have a great day, a good weekend, and we will see you next week to wrap things up.
Sure.
All right. See you then.
Okay.
Bye.
Mm.